Hey everyone, how's it going? My name is Sean, and this is a quick video that I put together to detail the differences between a linear and a nonlinear static structural simulation. This example covers both material nonlinearities as well as large displacement, which are probably the two most common reasons you will run a nonlinear simulation. So let's jump into the software and get started right away. In this example, we'll go ahead and start out with the linear static structural simulation. So first we have just this simple part where I am fixing this cylinder on the bottom and I'm pulling upward with a 100-pound bearing load. The material this part is made from is Delrin. So in this case it really looks only at the elastic modulus of the material to develop my stress-strain relationship. So what you're going to see is stresses that are much higher than could physically be in this part because Delrin yields at around 10,000 psi. So we'll go ahead and take a look at the material properties here. And for the linear simulation, what we really care about is this Young's modulus, also known as elastic modulus, and Poisson's ratio and things like that are linear elastic behavior. Now, for the nonlinear simulation, we're going to have to use the advanced properties here, where we actually look at a stress value for a given strain, and this is going to be based on an approximation of the stress strain curve for the series of Delrin that I'll be using. Now I will say this is a rough approximation. You can get a lot more detail in this if you have the data available, but for our case this was sufficient. So as you'd expect, in the higher strain regions, a nonlinear simulation is going to be a lot more accurate than a only linear simulation, just because a linear simulation assumes that beyond the yield point the behavior is still consistent and linear. So as I mentioned, we are fixing here and we're pulling up with 100 pounds. Now another thing about the linear structural simulation is it doesn't break the load down into steps, at least not in Fusion 360. Software like ANSYS will actually allow you to do that, but in this case I had to run a different load case for each load value. So that's why you see a couple different load cases. Now if we look at the results here, we see that the max stress is 33,318 psi. As I mentioned, that doesn't actually exist in the part because our maximum tensile stress is somewhere in the order of 10 to 11,000 psi. So we already know this is artificial. Now let's look at the displacement. We see that the max displacement at 100 pounds is 0.6 inches. And I'll compare that to the nonlinear here in a second, and you'll see there's a big difference. And when we go to strain, we only get a 0.12 strain. For this particular grade of Delrin, the strain to failure is approximately 0.25 or 25%. So we're going to look for anything over 0.25 to assess failure criteria. So this is telling me I'm only halfway to my maximum elongation to failure, and that's an absolute lie. Now let's take a look at the nonlinear static stress simulation and see the difference. So the first thing you should know is that a nonlinear simulation breaks the simulation down into steps. You see here 10 steps. This is a setting that you can define, but in our case this was sufficient. So if I apply 100 pounds, each step represents 10 pounds. So step 10 is a 100-pound load. Now you already see here the displacement is 1.55 inches, whereas if we go back to our linear simulation, my displacement was only 0.6. So it's almost an entire inch of additional displacement. The next thing we'll look at is our stress. Our stress flags out at a max of 13.8, which is a little bit incorrect, but it's a lot closer to the reality of the maximum stress that Delrin can bear. And if we look at our strain, we get a much different picture. We see a very high value, 1.691. Again, that couldn't happen. The max you can see is 0.25. So what I do in this case is I move my slider up to a minimum threshold of 0.25, and I start looking at where elements are above this value. So here you can see that at 100 pounds I have exceeded my 0.25 max elongation almost through the thickness of this part. We would undoubtedly have catastrophic failure at 100 pounds here. So if I want to guess about when this part will fail, I'll just walk through the steps until I think we've seen enough strain above the 0.25 mark that it would cause failure. So if I go to step 7, which is 70 pounds, we really don't see many elements at all above our threshold of 0.25. It actually doesn't even go much into an element. This is really a surface. I don't think it'll fail at 70, but this is the first point at which I would say we have a risk of initiating a crack. If we left it at 70 pounds for a long time, we would probably get creep and ultimate rupture, but not right away. Now, if I go to the 80-pound mark, step 8, I'm starting to see appreciable penetration into this thickness, right? This is probably 25% of the total thickness. So if I were interpreting this, I'd probably say 80 pounds is where I'd expect to see crack initiation. And as soon as that crack initiates, if the load's maintained, we're going to see catastrophic failure. And if we go to load step 9, undoubtedly, I would expect failure here as well. And as I mentioned before, load step 10 should be complete failure if we haven't already seen it. But my estimate is going to be closer to 80 pounds, where we start to see quite a bit of strain penetration above the 25% mark through this thickness. So now we're going to jump into a quick test setup I put together just to see how much load it takes to fail this part and approximately what the displacement is. Here's our simple test setup. What it is a linear actuator that's going to pull upward on our Delrin piece here, and I have a scale that's going to measure the load, and this flag right here next to a ruler so we can get an approximate displacement. Obviously this isn't going to be extremely high precision, but what we're really looking to see is if we're closer to the 1 inch that we predicted at 80 pounds with a nonlinear, or the ½ inch that we predicted with the linear. I think you can already guess the answer there, but we just needed a rough order of magnitude estimate here. And we'll go ahead and get started with the test, and I will slow it down at 80 and talk through the results there. So you can see that we started out just above the 7-inch mark. Now I've put the linear simulation at 80 pounds on the left and the nonlinear simulation at 80 pounds on the right, so that we can compare where the flag actually ends up when we hold here in a second at the 80-pound mark. And if we look back at our flag here, we can see that we are exactly where we expected to be with the nonlinear simulation. So we're just above 8 inches on the flag, so maybe we had an actual displacement closer to 1.1 inches, but I'd say we are exceptionally close, probably within 10 to 15% of our estimated value. And obviously our linear simulation on the left was just catastrophically wrong. We would never believe the result of a linear simulation with this much displacement. So let's continue. If you recall, I had estimated that we'd see failure at around 80 pounds, but we're slowly exceeding that. Now I've slowed the video down because I do expect it to happen really soon, and I'll just get quiet and let you watch the magic as this part breaks into several pieces. And there you have it, catastrophic failure right around 85 pounds. So now we can not just say that our displacement for a nonlinear simulation is much more accurate than a linear, but also our ability to predict the point of failure is also much greater with a nonlinear simulation. Of course, if you've done this before, you expect that, but if you've never seen the difference between the two, it's always important to remember that if you are dealing with large displacements, you really need a nonlinear simulation, and if you're running a simulation beyond the yield strength of the material, it is absolutely critical that you consider material nonlinear properties as well. So that's it for this video. I hope you got some meaningful information from this, and if you have any questions, always feel free to ask.